Okay, welcome to this video where we're going to be talking about a couple of important inventory models. We'll begin with the EOQ model. So let's set up some basic things that we need to talk about the EOQ model. So let's begin with the role of cycle inventory in supply chains in general. So when can you exploit economies of scale? When can you apply the EOQ model? There are three major scenarios where you can do that. One is when fixed cost is incurred each time you place an order. This is something that is very important to remember because the fixed cost is incurred irrespective of how much you order. So there are some economies of scale to be exploited there. There are a couple of other times when economies of scale can be exploited, which have to do with discounting, which we will talk about in the coming weeks, right? So right now, let's talk about the first scenario. And even here, we'll talk about the single product scenario. And next week, we'll look at the multiple product scenario, right? Okay. So when talking about the economic order quantity model, when talking about economies of scale, there are major costs that we have to figure out how these costs impact our inventory system. So when you're holding, when you have inventory, you incur inventory holding cost, you incur inventory ordering cost, that is the single order that you're placing, the cost that you incur there. And then of course the cost of the items that you're buying. So when you're calculating inventory holding cost in reality, how is it done? So one of the major aspects, one of the major parts of calculating inventory holding cost is calculating the cost of capital. How much does it cost us to hold the capital that we have? We either have it intrinsically as part of equity, as equity in the company that we have, or it is debt that we have borrowed from company. So that is what this equation is about. So this portion that you have, so E is the amount of equity you have, D is the amount of debt. So this is the percentage of equity that you have in your company, and this is the percentage of debt that you have in your company. So this is the percentage of debt times the rate at which you can borrow. So this is the rate at which the firm can borrow money. That's the percentage times 1 minus the tax rate. Obviously, you have to pay taxes on that. And then this is the equity times the returns that you can expect on the amount of equity that you have, right? So this is the volatility of the firm times the market risk premium. Those are things that you can calculate times the risk-free return that you have. So with all of this, we can calculate the cost of capital. And that is part of your inventory holding cost, because whenever you're buying inventory, you're buying it with either equity that you have already or you're financing it with debt. In either case, you need to know how much it's going to cost you to hold these items in inventory over the long term. So that's part of the inventory holding cost. So apart from that, the other things that go into inventory holding costs are occupancy costs. This is something that I talked about in the last video. You might have rent, you might have electricity. So if you're storing inventory, you might have to pay rent for the place that you're storing. Electricity, you might have a security guard outside, you might have special things that you need to do, like say we might have a refrigerator, and so you might have some maintenance costs for the refrigerator. You might also have handling costs. Maybe you need hazmat suits, or you need people trained in with hazmat stuff to handle your inventory. Or you have obsolescence costs. You're holding inventory for too long. Either the item that you're holding either goes out of fashion and then you have to sell it at a lower price, or it goes bad. So if you're holding perishable items in inventory, sometimes the items will perish. So apart from that, you also have theft, security, damage, tax, insurance. So lots of other things that go into calculating inventory holding costs. But at the end of the day, it's calculated as a percentage of the price that you pay to buy the item, right? Or make the item, depending upon which scenario you're looking at. Now, the other cost is ordering cost. So this is a one-time cost that you pay to order each lot that you order, and that is based on the buyer time. So how much time did I spend going through this? Transportation costs. So whether you order a single item or 10 items, it still has to be transported on a truck. So there are fixed transportation costs, there are fixed receiving costs, and there are other costs also that are fixed. You might hire an accountant to do something, and whether, again, it's a single item or 10 items, the accountant might charge you the same amount of money, right? So all of this go into fixed ordering costs. right? So here are a few things that we're going to look at, some parameters that we're going to look at to go over the economic order quantity model. So D will be the annual demand for the product, S will be the fixed cost that is incurred, C will be the unit cost, the cost per unit, and H is the holding cost per year as a fraction of the cost. So when you say holding cost per year, it'll actually be H times C. It's the percentage of the price of the item, right? Now there will be some assumptions that we'll make, which might seem like it's making the model very simple, but actually in reality it works really well. One is that demand is used at a steady rate per over a unit time. Now this is not a bad assumption to make. If you are looking at annual demand, it might be that, let's say that you have a demand of salt, which is at 100,000 units of salt will be sold over the next 6 months, next 10 months. It doesn't mean that you will sell exactly 10,000 units per month, but for planning purposes, unless you have some sort of seasonal variation, which is unlikely, especially given for a commodity like salt, you can assume that you will sell about 10,000 units per month over those 10 months. So you can plan for 10,000 units per month, right? So that's the assumption that we are making. Now, we are also going to make the assumption that shortages are not allowed. That is, if you're short any units, nobody will buy it from you. They'll go somewhere else and buy it, because sometimes you can have back ordering. So if you are selling items that are very specialized, say for example, if you're selling cars and somebody wants to buy specifically a black Beamer with a certain packages or leather seats and all of those things, they are looking for a specific item. So if you don't have it on your lot, they will order it from you and wait for you to bring it and deliver it to them. So that is a backlog. That's a back order, right? So we are assuming that back orders are not allowed here, and that replenishment lead time is fixed. In fact, when we talk about safety inventory, which is the next chapter, we'll mainly be relaxing this assumption that replenishment lead time is fixed. We'll also be relaxing this assumption that demand is steady, but that's the interesting piece that we'll talk about in a couple of weeks, right? Okay. So our objective is to minimize the total cost, the cost of material, cost of ordering, and the cost of handling. So given all of the assumptions that we've made so far, what does this cost look like? So let's go through each of these step by step. So first is the annual material cost. Annual material cost is just C times D. Because remember, we're calculating this for the whole year. It doesn't matter how the inventory gets used. You're assuming that demand for the whole year is capital D. So capital D times C tells you this is the cost of all the materials that you're going to buy for the whole year. C is the cost per unit, D is the annual demand. Now, with that, how many orders will be placed in a year? Now, it's D over Q. So why is it D over Q? So D is the annual demand. Q is the lot size. So this is how many units you'll be ordering each time you place an order, right? So capital D divided by capital Q. So if your demand is say 1,000, and every time you place an order, you order 100 items, right? You're going to be placing 10 orders in a year. So you're going to order 100, 100, 100, 100. You're going to order that 10 times. Why 10 times? Because over 1 year, you need 1,000 items, right? So 1,000 divided by 100 gives you the number of orders you're going to make in a year. So the total annual ordering cost will be the number of orders you make times the cost of placing a single order. That is what capital S is, the cost of placing a single order. So this is the number of orders times the cost of placing a single order. And the annual holding cost is the average inventory that you have times the holding cost. And remember that we're writing unit holding cost as capital lowercase h times C, which is the percentage of the price that you pay to buy the item. So the total cost will be the material cost plus the ordering cost plus the holding cost. So this is average inventory times the cost of holding that inventory, right, per unit. Now, few things to keep in mind. Now, whenever you actually do the calculation for this, and we'll do that in a second, you will notice that the material cost tends to be much higher than the ordering and inventory and holding cost. So just the holding and ordering costs together are called inventory related costs, because it's not material cost is not exactly inventory related cost, not directly. So sometimes it's just called inventory related cost, but that's something to keep in mind. Right? Okay. So if you look at the ordering cost, holding cost, this is what the curves look like. Let's see why. So if you look at the material cost is C times D. So that's a fixed number. So it's a single fixed number. That is why this is the line representing the material cost. It's fixed. It doesn't change with the lot size. So if your annual demand is 1,000, you are going to buy 1,000 items at some point in time. So how many items you order each time has no bearing on the total cost of the materials, right? Next is the holding cost. So holding cost is H times C times the number of units that you order divided by 2, right? If you go here, it is H times C times Q divided by 2. So it is linear in the number of items that you order. So that's the straight line here. So that's the number of items you order. As you order more and more items, you'll be holding more and more inventory. So your inventory holding cost will go up. As opposed to that, if you look at the inventory ordering cost, the inventory ordering cost will go down as the lot size increases. So lot size represents the size of the order every time you place an order. And the assumption is that the lot size will remain fixed. So if the lot size is very small, it means that you'll be ordering multiple times in a year. So the best way to compare this is if your annual demand is 1,000 and your lot size is 10, which means that you'll be ordering 100 times in a year, right? If you're ordering just 10 items each time, you have to place 100 orders. So the total cost of ordering will be 100 times the cost of ordering, right? As opposed to if your lot size is 100, then you'll only be ordering 10 times in a year. In that case, the total cost of ordering will be 10 times the ordering cost. So that's why that is reducing in the lot size. The lot size is larger, your ordering cost will be lower, but your holding cost will be higher. And that's the balance that you have to strike, right? If the lot size is too large, you'll have very high holding costs, even though the ordering cost is low. But if your lot size is too low, your holding cost will be low, but your ordering cost will be high. So if you look at the total cost curve, there is this particular point here where you have the minimum value for total cost. So this value for lot size minimizes your total cost. And that is exactly the point where the holding cost and the ordering cost are equal to each other. So if you say that's the point where holding and ordering costs are exactly equal to each other, right? So if you look at that, the holding cost is D times Q over S, and the ordering cost is D times Q over S, and the holding cost is Q over 2 times H times C. So if you set these two equal to each other and you solve for Q, you can find out what the optimal ordering quantity is. What is the economic ordering quantity? How much should you order so that the total cost is minimized, right? And that is this formula, right? So this formula comes exactly from setting the ordering cost equal to the holding cost. So that's very simple algebra. You set them equal to each other. In one case, Q is in the numerator. In another case, Q is in the denominator. So when you cross multiply and everything, you get Q squared equal to something. Then you take the square root. And this is what you'll end up with. So this is the optimal lot size, the economic order quantity. It is the square root of 2 times D times S over H times C. Very important things to keep in mind. Ordering cost is cost per order. So it's not based on time. It is based upon the cost of placing a single order, right? Now, capital C is the cost of a single unit, right? So that doesn't depend upon time either. So demand is the annual demand. So that's demand for the whole year. The only thing that depends upon time essentially is H, which is the percentage, right? Even that doesn't directly depend upon time. So the optimal lot size is square root of 2 times D times H over H times C. With this, we can calculate the number of orders that you place in a year, which is D over Q, which is what we had, right? So annual demand divided by Q, and that will be square root of D times H times C over 2 times S. So sometimes this will be just as important as that, right? Okay, so let's look at a simple example. And I'll end this video here, and then I'll make a different video where I'll talk about the production lot size model. That'll be a much smaller video. All right. So the annual demand, so let's assume that we are selling an item where selling a computer where the annual demand is 1,000 units per month, or monthly demand is 1,000 units, or annual demand is 12,000 units for the year. Now the cost of placing an order is $4,000. So every time you place an order, you have to pay $4,000. Now, why is the cost so high? Because it includes transporting all the computers to your from your supplier to your shop, so that definitely takes some time. And then there is the unit cost per computer, so you're paying $500 to buy the computer, and the holding cost per year as a fraction is 20%. So you're saying that I'm paying $500 to buy a computer, and my holding cost is going to be 20% of that $500, right? So 20% of the $500, which is 20% of $500, will be $100. That's your holding cost, 20% of that. So your optimal order quantity will be 2 times D times S divided by H times C, and this will turn out to be approximately 980 units, right? And that's the optimal order quantity. So every time you place an order, you have to order 980 units. Now, before I end this video, a couple of things I'm going to talk about. So this solution here is robust. What this means is that if you look at the cost curve here, you'll notice that the lowest value was here. So if you order 980 units, your total cost gets minimized. But if you order slightly more units, your cost will be higher, but the closer you are to 980, the better your cost is going to be. What does this mean? This means that if your optimal order quantity is 980, but you can only say order in lots of 100. So maybe you can't order 980. So maybe then you order 1000. So 1000 will definitely not be the optimal order quantity, but it is the best you can do given the other constraints. So that is still okay. So the closer you are to that number, the better your answer is. So that is what you mean by the thing being robust. So sometimes these curves can be really wonky and your results are not robust, but this is an example where your result is robust, right? So that's the optimal order quantity. And the cycle inventory is half the optimal order quantity, which is 490. And the number of orders that you can place in a year will be 12,000 divided by 980, which is 12.24, which means that 24% of the 13th order will be accounted for in this year, and the remaining 76% will be accounted for in the next year. And the total annual ordering and holding costs will be D over Q times S plus Q over 2 times HC, and they'll add up to 97,980. In fact, if you calculate these costs individually, it will be exactly half of each. Because remember, when we calculated Q star, we set this value equal to this value to calculate the value of Q star. So if you calculate this cost and you calculate this cost, it will be exactly half of this cost, right? And finally, the average flow time. The average flow time is Q star over 2 times D, which is 0.49 months. Because everything is months here, about half a month, right? So a couple of weeks or however you measure time. So this is going to be about half a month, right? Okay. So I'm going to end this video here. We're going to continue with a lot sizing in the next time. We'll look at production lot sizing. So this is an example where we placed an order and we received the whole order at once. But what if we have to make the items ourselves, right? So that's what we'll talk about in the next video, right? Take care.